Now we'll see how to represent a heap tree. We know that heap tree is a complete binary tree, and we have seen that sequential representation is good for complete binary trees. So we'll represent our heap using sequential representation. In sequential representation, we take a one-dimensional array and store the root of the tree at index 1 of the array. Left child of a node that is at index I is stored at index 2i of the array. Right child of a node that is at index I is stored at index 2i plus 1 of the array. And parent of a node that is at index I is stored at index floor I by 2. We'll maintain the size of a heap in a variable. Suppose n denotes the heap size, and this array A is used to implement the heap. Then the elements from A1 to AN represent the heap values. The values of this array after this index n may contain valid entries, but they are not part of the heap. Only this portion of the array represents the heap. We'll use this index 0 of the array to store a sentinel value. Now here, if this 2i is greater than heap size, it means that left child of node n does not exist. And if 2i plus 1 is greater than heap size, it means that right child of node n does not exist. This is a heap tree of size 12 and it is represented using this array. We can see that the root node is stored at index 1 of the array. Now for this node, I is 6 and 2i plus 1 is 13, which is greater than the heap size. So we can say that the right child for this node does not exist. For this node, I is 7, 2i is 14 and 2i plus 1 is 15. Both are greater than the heap size. So we can say that both left and right child don't exist for this node. Now in this index 0, we'll store a very large value that will be greater than any key value possible in the tree.